All right, so now we want to discuss the concept of torque. Torque is going to be what is going to cause something to rotate. A force, F, is what's going to cause an object to move sideways. So forces cause things to move linearly. Torques are going to cause things to twist, to rotate. So we're going to symbolize torque with the letter T. So you'll notice that, and this is a Greek T called tau. So you'll notice that when we describe rotating objects, we tend to use Greek letters to do it. And so torque T is going to be related to force. But the connector between linear concepts and rotational concepts is going to be the radius. So that the larger the handle on a wrench, the more torque you can apply. So this is the force that you're applying. This is the radius at which you're applying the force. And then this is the amount of twist that you can apply. And so it has a red box around it. So I would like for you to be able to do it. So here is a torque wrench. And the question is, what happens if you want to triple the amount of torque? What could you do? So this needs to be 3 times as much. So what could you do to this side so that it's 3 times as much? Well, you could be 3 times the handle, or it could be 3 times the force. And then here's one where you're actually plugging numbers into the formula to actually calculate a torque. Okay, then we had Newton's laws of motion. So the stuff that's in the green, don't worry about it. It's not going to be on the exam. But the stuff in the orange, you do. So all you got to remember is what was Newton's first law of motion. An object in motion stays in motion at a constant speed forever and ever in a straight line. Well, the rotational counterpart to it is almost exactly the same. An object that's spinning wants to continue to spin forever and ever at a constant speed, but the difference is the axis of the rotation always wants to point in the same direction. And so you can look on the internet and find a video where it shows somebody holding a wheel, and then the wheel is rotating like this, and then they try to do this. And they say it's hard to do it. So it's hard to rotate that wheel to get that axis to change. So the wheel is rotating like this, and it's hard to twist it like this because the axis always wants to point in the same direction. A really good example of this was, remember what it was like trying to pedal a bicycle for the first time. And did you notice that it was much easier to stay upright on your bicycle once you got going? So once you got going, what were the wheels doing? They were spinning faster. And so the faster they're spinning, the harder it's going to be to change the axis of that wheel. So that's what keeps you upright. So the faster that you're going on your bicycle, the less likely you are to tip over. Then his second law, okay, so let's go back to linear concepts. His second law was force equals ma. So the pusher makes the system accelerate. So the rotational counterpart would be the twister. So the torque is going to make the system accelerate. But instead of being a linear acceleration A, it's going to be a rotational acceleration alpha. So here is an example of the kind of question I could ask you. If you apply twice the amount of torque on a wheel, what will happen to the angular acceleration? So we're dealing with torques, and it says something about acceleration. So what's the only formula that we have that has a T for torque in it, and then it also has an acceleration alpha? Well, there's only one formula, so it's got to be this one. And so it says that if we're going to apply twice the torque, so 2 times the T, what will happen to the acceleration? So nothing's happening to the I, because the I depends on the object, and we didn't change the object. So therefore, it has to happen to this thing. So if this is 2, this side over here has to be 2. And then you've got the third law. For every action, there's an equal and opposite reaction. So for every torque that's going this way, it's going to cause a counter torque in the opposite direction. And so we did an example with the helicopter, and so this would make for a good essay question. So if the tail rotor of a helicopter gets hit so that it stops working, what will the helicopter do and why? And so you would include this idea of for every action there's an equal and opposite reaction in your answer to that question. Okay, this is rotational equilibrium, which will not be on the exam. So let's not worry about summing the torques acting on a system. So that's not going to be on the exam. Okay, let's take a break. When we come back, let's talk about momentum.